Hello everyone, my name is Farsh and I'm going to provide a series of lectures on multivariable calculus. And this is how I'm going to provide the lectures. I'm going to provide a series of theory lectures that will contain most of the theory and some examples. Whereas after the lectures, I will also provide a tutorial which will have most of the things that you require to master the concept. So let's start with something that I would like to call lecture 0 that has the notations that I'm going to use. Some of them, at least. So first I'm going to start off with the concept of Rn, and then I'm going to come to the concept of the scalar product. And once I finish that, I'll go to the concept of the Euclidean norm. Okay, so let's start with the concept of Rn. So what exactly is Rn? Well, to make things simpler, I'll provide an example. So consider a point, say somewhere. And suppose you can express that point in terms of its three coordinates. So yeah, you have something like x, y, and z. And so you have three axes, x, y, and z. Now, a set of all points that can be expressed in terms of three coordinates forms a set that's known as R3. So I like to think of R3 as a set. Now, similarly, you can also generalize this statement. Why should we only have three coordinates? What if each point can be described by n coordinates? Something like, say, x1, x2, up to xn. So the set of all points that can be described with n coordinates forms a set of Rn. So this is what Rn really is. Now let's come to the second concept. Um, just to mention, Rn does have a few properties which I'll come to in the tutorial. Okay, so now what is a scalar product? Well, consider two vectors. Call them A and B, capital A and B. And suppose these vectors belong to the set of Rn. And say A is equal to something like A1, A2 up to AN, and similarly B is also equal to B1, B2 up to Bn. So A dot B, so when I say A dot B, I mean the scalar product of A and B. So the scalar product of A and B, or A dot B, is equal to, by definition, A1 B1 plus A2 B2 plus so on to A and Bn. So you sort of multiply the first coordinates of the two vectors and add that to the product of the second coordinate, the product of the second coordinates of A and B, and so on. Okay, so now the scale product does have a few properties as well, which I'll get to later. Next, let's talk about the Euclidean norm. So the Euclidean norm, by definition, so say we have a vector A that's again a part of Rn. The Euclidean norm of Rn of A, sorry, is equal to the square root of A and A, scalar product of A and A with itself, and the square root of that. So you have something like the square root of A1 up to AN, or with the dot product with 1 up to AN. So if you expand this, you'll get something like So this is the Euclidean norm. It's worth noting that in R2, so when each point can be expressed as expressed in two coordinates, so that would be, say, the xy plane. Suppose you have a point x1 and y1. So the Euclidean norm in this case of, say, a is equal to the root of x1 squared plus y1 squared, which is equal to the length of the vector that starts from 0 and goes to x1, y1. Similarly, in 3 dimensions, you have root of x1 squared plus y1 squared plus z1 squared if the point is x1, y1, and z1. And say this is b. So the norm of b is equal to x1 squared plus y1 squared plus z1 squared, which is equal to the length of the vector which starts from 0, 0, 0 to x1, y1, and z1. Okay, so that's it for this video. In the next video that I'll post probably in this week, I'll provide a tutorial which will have examples and some properties related to the notations that we learned today. And in the next lecture that I'll post next week, I'll give a lecture on functions that go from the set of R to the set of Rn. So yeah, that's it for today. Thank you for watching, and I'll see you next time.